Welcome back to the deep dive. You know the drill. We take a pile of research, articles, notes, and boil it all down for you, our curious listener. Today, we're plunging into a world that's often hidden, but honestly super important. Submerged arc welding. But we're not just scratching the surface of the process itself. Nope. Our mission today is to really peel back the layers on its, essential consumables, the welding wires and the powdered fluxes. These aren't just, minor add-ins. They pretty much dictate the quality, the performance, even whether a weld is feasible at all. It's kind of a hidden world of science, and getting a handle on it is, I think, a shortcut to understanding the integrity of these huge structures all around us.
It really is. And what's fascinating here is how these things that seem so simple, just a wire, right, or a granular powder, are actually meticulously engineered. Choosing the right ones, handling them correctly. It's absolutely critical to the integrity and the lifespan of the final weld. I mean, when you're talking about massive structures, ships, bridges, pressure vessels, the smallest detail in these consumables, it can have huge real-world consequences.
It really makes you wonder how much thought goes into something we barely even register. Okay, so let's start that first unsung hero then. The wire electrode. You called it the metal backbone. So what exactly is this wire fundamentally?
Fundamentally, it's simply the continuous bare wire that gets fed into the welding arc. As it melts, it becomes the main filler metal. It literally forms the new material that joins the parent metals together. It is the weld, essentially.
Right, it becomes the joint. And I'm guessing it's not just one size fits all. There must be different wires for different jobs.
Oh, absolutely.
Yeah.
You mainly run into two types, solid wires and metal cord wires. And the range of materials they can handle is, pretty extensive. Solid wires are used for everything from your standard carbon steels and low alloy steels, all the way to high-performance materials like creep-resisting steels, stainless steels, even nickel-based alloys. And there are also special alloys just for surfacing, cladding a base metal to boost its wear or corrosion resistance. Think like the edge of a digger bucket or maybe reinforcing a railway track.
Okay, now here's where it gets really interesting for me, something I noticed in the research. Those common carbon and low alloy wires, they almost always have that copper coating. My first thought is, isn't that just extra cost, an extra step? Why bother with what seems like such a tiny detail for something that's just going to get melted down anyway? What's the, the engineering magic there?
That's a really good question, and it perfectly highlights how much subtle engineering goes into these things. That thin copper coating, it actually serves three vital functions. Without it, the whole operation would be, much rougher.
Three.
First, it makes sure there's good electrical contact between the wire and the contact tip. That's crucial for a stable arc and, consistent melting.
Right, electricity needs to flow smoothly.
Exactly. Second, it helps the wire feed smoothly through the whole system, the guide tube, feed rolls, contact tip. It cuts down friction, which also means less wear and tear on the contact tube itself.
Ah, okay, so it prevents jams and things.
Pretty much. Imagine a wire constantly snagging or dragging. That's what you'd risk without the coating. And third, that copper provides a really important layer of protection against corrosion, against rust forming on the wire before it's used.
So it keeps it clean?
Keeps it clean and ready. So yeah, it's like the silent foundation for operational reliability. Turns potential chaos into a smooth, predictable process.
Wow. So that tiny copper layer is doing a massive amount of work, impacting the actual welding process directly. And it makes you think, if that much care goes into the surface of the wire, how critical is its overall condition? Which leads us perfectly to storage and care, doesn't it? Because weld quality and smooth operation really hang on this.
They absolutely do. The main takeaway, the simplest rule is keep the wires clean, free from oil, dust, any contaminants. The dangers if you don't, they're pretty significant. Take rust, for example. Big problem. Why? Because it's hygroscopic.
Hygroscopic, meaning it absorbs moisture.
Exactly. It pulls moisture right out of the air. If that moisture gets into the weld, it can lead to a really critical defect called hydrogen-induced cracking. Very bad news for the final weld strength.
Okay, hydrogen cracking, got it.
And besides the chemical risk, rust physically messes things up too. It stops the wire from feeding smoothly, causing interruptions and potentially poor welds. Same goes for any mechanical damage, kinks, bends, that kind of thing. It just won't feed right.
And what about other contamination, like grease or paint?
Yeah, that's a nightmare, especially for ferrous metals. For steels, contamination from carbon-containing stuff, oil, grease, paint, even those lubricants used when drawing the wire is particularly harmful. When that extra carbon gets into the weld metal, it changes the weld's properties, usually not for the better. And maybe even more dangerous, it can help hydrogen get absorbed into the weld pool. Again, risking that hydrogen cracking.
So it circles back to the hydrogen issue again.
It often does. That's why following the manufacturer's recommendations for storage and handling isn't just, a suggestion. It's absolutely non-negotiable if you want weld integrity and safety.
Okay, so the wire, metal backbone, carefully engineered, needs meticulous handling. Got it. Now let's shift focus to the other unsung hero, the real secret sauce of SA, the flux. What is this granular stuff that gives submerged arc welding its name?
Right, the flux. It's essentially a granular mineral compound mixed to very precise formulations. Its main job, the reason for the name, is to literally submerge the arc. It creates this protective blanket covering the whole welding zone.
A blanket, okay.
Yeah, it shields the molten weld pool from the atmosphere, keeps oxygen and nitrogen out. When it gets hot, it transforms, producing both shielding gas and a layer of molten slag on top of the weld.
Okay, so protection from air is key. But you mentioned it does more than just that. What else is going on under that blanket? What's maybe the most surprising function?
You're right, it's much more than just a passive shield. It's very active. While protection is vital, the flux also actively cleans the molten weld pool, pulling out impurities. And here's where it gets really clever, maybe the most surprising part. It can actually change the chemical composition of the weld metal itself.
Wait, a flux changes the metal. How?
Through chemistry. Deoxidizers and specific alloying elements can be deliberately added into the flux formulation. As the flux melts, these elements transfer into the weld pool, adjusting the final chemistry.
Wow, okay.
It also helps control the heat, preventing it from escaping too quickly, which affects the cooling rate and the final microstructure.
Yeah.
And it even influences the shape of the weld bead through something called its wetting action. Helps get that nice, smooth profile.
So it's cleaning, controlling heat, shaping the bead, and actively adding ingredients to the metal. That's way more than just a shield.
Exactly. Its ability to fine-tune the chemistry and shape is probably its most critical and perhaps unexpected function.
Fascinating. So it's not passive at all. Okay, and just like wires, I assume there isn't just one kind of flux. We need to dig into the types, right? Let's start with fused fluxes. How are they made, and what makes them different?
Right. Fused fluxes, the production process is key here.
Oh.
You take the raw mineral constituents, dry mix them, and then melt them all together in an electric furnace at very high temperatures. Then this molten mixture is rapidly cooled, often by pouring it into water or onto ice, which creates glassy granules. These are then crushed and screened to get a uniform glass-like product.
Glass-like. Okay, so what does that mean in practice? What are their characteristics? What does a welder see and experience?
Visually, yeah, they look like crushed glass, often glossy, hard, maybe black, sometimes flaky. For the welder, this consistent glassy nature translates into some real advantages. Fused fluxes are known for giving a really stable arc.
Okay, stability is good.
Very good. They also tend to result in a better-looking weld bead, and the slag layer usually chips off more easily afterwards. Plus, their consistency often allows for higher welding speeds, which helps productivity.
Nice. Any other pros?
Chemically, they're very homogeneous. The composition is uniform throughout each particle in the whole batch. And importantly, they are less hygroscopic than other types.
Less hygroscopic, so they don't absorb moisture as easily.
Correct. That makes handling and storage much simpler. They might pick up some surface moisture, which needs drying off, but they don't soak it up deep inside like some other types. Also, because they're hard particles, if some break down into fine powder fines, you can remove those fines without really changing the flux's overall chemical composition, and they recycle well through the feeding system.
Okay, so consistent, stable arc, easy slag removal, faster speeds, less moisture worry. Sounds pretty great. But engineering is always about trade-offs, isn't it? What are the downsides, the limitations?
You hit it exactly. Trade-offs. One major limitation is composition. Because of that high melting temperature during production, some useful ingredients just can't survive the process. Things like basic carbonates, for example, break down.
Ah, so you're limited in what you can put in them.
Precisely. This also makes it difficult or inefficient to add things like deoxidizers or ferroalloys directly into fused fluxes. They might segregate or get lost during the melting.
Right.
So that ability to fine-tune the weld metal chemistry through the flux, it's quite limited with fused types. And they also tend to be what we call acidic type fluxes, which for certain high-spec applications might not provide the absolute highest toughness or crack resistance compared to more basic fluxes.
Okay, limited chemistry control and potentially lower quality for some demanding jobs. That leads us perfectly to the next type, then. Agglomerated fluxes. How are these different? Production, characteristics, trade-offs.
Agglomerated fluxes use a totally different manufacturing process. Instead of melting, the powdered raw ingredients are dry mixed and then bonded together using a binder, often a silicate solution like potassium or sodium silicate.
So they're stuck together, not melted together.
Exactly. This wet mix is pelletized, then dried at a lower temperature, crushed, and screened to the right particle size. Visually, they look different too, usually dull, irregular shapes, and they're more friable, meaning they crush more easily. They have a granulated look.
Okay, different look, different process. What's the big advantage here, especially thinking about that chemical modification issue with fused fluxes? This sounds like it might be the solution, but I bet there's a catch.
There is, but the advantage is huge. Their most crucial benefit is exactly that chemical control. Because they're made at lower temperatures using binders, you can easily add those important deoxidizers and alloying elements during the mixing stage. This gives you incredible flexibility to precisely adjust the final weld metal composition. That's a massive plus for critical applications needing very specific properties. They also tend to allow for a thicker flux layer during welding, which can be helpful. And welders often find they give high weld quality, maybe lower flux consumption, easy slag removal, and a nice smooth weld profile. You can often tell them apart by color and shape, too.
Okay, precise chemistry control. Good weld quality. That sounds like the winner. What's the catch? You mentioned a catch.
The catch is significant, and it comes back to moisture. Agglomerated fluxes are generally much more hygroscopic. They love to absorb moisture from the air, and not just on the surface, it gets absorbed into the particles.
So much worse than the fused type for moisture.
Much worse. This makes baking them to dry them out quite difficult, sometimes impractical. They need really careful storage and handling, very similar to how you'd treat low-hydrogen basic stick electrodes. Strict drying procedures are essential before use.
Right, so that precise control comes at the cost of needing extreme moisture discipline. Any other downsides besides the moisture sensitivity?
Yes, a couple.
Yeah.
Because of the binders and the lower processing temperature, some gas can evolve from the flux as it melts during welding. If not managed properly, this can potentially lead to porosity, little gas bubbles trapped in the weld.
Porosity, okay. Not good.
Not good at all. And there's also a slight risk of changes in the weld chemistry due to segregation. Because the particles are more friable, handling can create fine dust. If these fines have a different composition from the main granules, and they get separated out or concentrated in the feeding system, your final weld chemistry might drift slightly. Maintaining that absolute consistency requires care.
So more control, but you trade ease of handling and gain risks of moisture pickup, potential porosity, and maybe some consistency challenges with fines. It's complex. Okay, so we have fused. Glassy, stable, less hygroscopic, limited chemistry control. Agglomerated, granular, great chemistry control, but very hygroscopic and needs careful handling. Then there's a third category mentioned, mixed fluxes. Sounds like trying to get the best of both, but I'm sensing a big but coming.
There is indeed a significant but. Mixed fluxes are exactly what they sound like. A physical mixture of two or more different fused or agglomerated fluxes blended in a specific ratio. The idea is to achieve a specific combination of properties, maybe for a highly critical or proprietary welding job, where no single standard flux quite fits the bill.
Okay, a custom blend. What's the problem?
The main problem is segregation. Big time. Because you're mixing potentially different types of particles, different sizes, densities, shapes, there's a huge risk they'll separate out during shipping, storage, even just sitting in the hopper.
Ah, like shaking a box of cereal and all the small bits end up at the bottom.
Exactly like that. And it gets worse. More segregation can happen in the flux feeding and recovery systems during the actual welding. So the flux going into the arc might not have the intended ratio anymore. This leads to inconsistent weld properties, which is precisely what you don't want in critical applications. Maintaining that consistent blend from mix to mix and all the way to the arc is a major ongoing challenge. It's a very tricky balancing act, used only when absolutely necessary.
Wow. Sounds like a high wire act, really. High risk if not managed perfectly. Which brings us right back to the practical side. General flux care and storage. Just like the wires, it seems absolutely paramount for all flux types. And this really raises that important question. Given all these different types, characteristics, challenges, how do welders actually choose the right flux? And crucially, what happens if they get it wrong?
Choosing is paramount, absolutely. Yeah. It depends heavily on the base metal being welded, the required mechanical property strength, toughness, corrosion resistance, the welding position, the joint design, and the overall service conditions the welded structure will face. getting it wrong, well, that can range from poor weld appearance or difficulty welding, right up to insufficient strength, lack of toughness, or even catastrophic failure due to things like cracking.
So the stakes are high.
Very high. Which is why the key practices for care are so rigorous. Rule number 1, keep fluxes warm and dry. Always. This is critical to prevent moisture pickup, which, as we've said, leads to hydrogen and the risk of porosity or cracking. Even those less hygroscopic fused fluxes can hold surface moisture, so they often need a quick drying bake. Agglomerated fluxes with that chemically bound water potential, they need even more careful treatment, often specific drying cycles at specific temperatures, just like basic stick electrodes, before they even go near the welding machine.
Okay, warm and dry is the mantra. And can you just keep recycling flux forever? I imagine it breaks down or gets contaminated eventually.
You're absolutely right. You can't recycle it indefinitely. As the flux gets used, handled, recovered, particles break down. If they become too fine, the flux won't flow properly through the feeding system it packs together. Also, repeated cycles can lead to contamination or subtle changes in composition. So for high-quality, critical work, you typically don't rely on 100% recycled flux. New flux is constantly added to the recycled batch to maintain consistency and performance standards.
Makes sense. Maintain the quality.
And just like the wires, basic handling matters. Don't dump bags from a great height, stack them carefully, keep them sealed until use. All common sense, but vital to maintain the integrity and prevent contamination or damage. It's a continuous process of quality control, really.
Okay, so let's tie this all together. What does this deep dive into wire and flux really mean for you, the listener? We've unpacked the copper coating, the fused versus agglomerated versus mixed fluxes, the critical need for careful handling. It means that this secret sauce we mentioned, it's not magic at all. It's actually precise formulation, precise engineering with very specific consequences that directly impact the strength, the safety, the integrity of massive structures all around us, bridges, ships, pipelines, you name it. These unsung heroes are doing some heavy lifting.
Absolutely. If you connect all these dots to the bigger picture, that choice, the right choice, and the meticulous care of these consumables, it directly influences everything. The mechanical properties, how the weld looks, and ultimately, the performance and safety of these huge structures. Think about it. A seemingly small mistake in storage, letting moisture creep into the flux, letting rust form on the wire, could genuinely lead to hydrogen-induced cracking. That compromises the entire structure.
And leads to potentially catastrophic, incredibly costly failures.
Exactly. It really underscores how crucial these seemingly small, often hidden components are in large-scale engineering. They demand precise attention right from the very beginning.
That is a perfect summary of why these unsung heroes truly matter. We've taken quite a deep dive today into this really nuanced world of saw welding consumables. The wires, the fluxes often overlooked, but as we've heard, fundamentally critical to the success of submerged arc welding. And it just reinforces that idea, doesn't it, that understanding the granular details is so often the key to being truly well-informed, whatever the field.
It really does. And maybe it raises a broader question for you, the listener, to think about. In this world just overflowing with information, with complex systems everywhere, how much attention do we really pay to the consumables? The foundational, often hidden elements that underpin success, not just in welding, but in any area of expertise you might be exploring. Are we always looking closely enough at those foundations?
That is a great thought to leave everyone with. Thank you for joining us on this deep dive. We hope you'll continue your journey of discovery with us next time.